Hey students, we are going to make some notes today over the characteristics of ionic bonding. You should have a piece of paper folded into the Frayer model. If you do not, real fast, you take your paper, you fold it in half, and you fold it in half, and then you find the corner that is not have any of the openings, total folds there, and you fold that corner in. So it looks actually like a little document icon you might see in Word or something like that, okay? The point is that when you unfold it, it's going to look like the picture on the screen where you have a diamond in the middle and you have 4 quadrants around, and that's what we're going to be taking our notes on today. So in the middle of our diamond there, you're going to write ionic bonding. This page of notes is going to be for ionic bonding. And you're going to, after writing ionic bonding there, we're going to go through 4 topics, and you have 4 quadrants, and you're going to work it out that way. Now, I want to warn you in advance, as you're writing down ionic bonding in that diamond, that I'm going to have a lot of words on the slides, and I do not expect you to write it word for word. That is not the point of note making. So after I go through what's on the slide, I will be sure to point out to you the important things that you definitely want to make notes of in that quadrant. So be sure that you kind of wait and follow along with me and then listen to what I say is important enough to write down in your notes afterwards. Okay, so pick a quadrant. Our first quadrant, whichever one you pick, is composition of the bond. So you'll want to title that quadrant composition of the bond. And we're going to talk about what makes up an ionic bond. And we're going to do this kind of notes for ionic, covalent, and metallic. And each one's going to have those 4 quadrants, and it's always going to be the same so that you can get a good comparison and contrast between the different note pages. So composition of the bond is this quadrant. Okay, so ionic compounds are composed of positive and negative ions. Ionic bonding made of ions. Hopefully not shocking, okay? Cations and anions are the vocabulary words that we have used before with that. And you want to be sure that you have those in your head because those are review words. They're going to be electrostatically attracted. Now, why does a cation stick with an anion? Well, you're saying because they're oppositely charged, opposites attract, right? 2 positives, they would not attract. 2 negatives, they would not attract. But a positive and a negative attract and they stick together. So an ionic bond is made of 2 atoms that are oppositely charged, literally magnetically sticking together, okay? They're going to do that in a ratio that makes the total of the compound zero out. And when we go to drawing, that's when this will make more sense. So just kind of like hang out with me on the idea that they're going to zero out overall in the end. Now, what should you write down? I would strongly recommend that you write down that an ionic bond is made of cations and anions. And if you don't remember that cations are positive, then maybe you like write a little positive there by cations. And if you don't remember anions are negative, maybe write a little negative there by anion, something like that. And then do be sure you make mention that the total of our cations and anions are going to zero out. That's not something important right at this moment, but in just a little bit as we start drawing ionic compounds with Lewis dot diagrams, we should see that those charges zero out. The positives and the negatives, there's enough of each to zero out the compound. Okay, I'm going to clear and same quadrant still, okay? I want you aware that ionic compounds are usually going to be crystals. So if you see something out there that's a crystal, I want you thinking ionic compound. So go ahead and write that down in your notes that ionic compounds are crystals. Okay. A crystal, if you're unaware, is a 3-dimensional network of positive and negative ions. So let's talk about this a moment while you write down that ionic compounds are crystals. So I have a sodium ion here, and I have a chloride ion here. And the sodium, being a metal and low in ionization energy, is going to lose an electron to the chlorine, which is high in electron affinity. And so they're going to move an electron. And the sodium then is positive and the chlorine then is negative, and the opposites are going to attract. Now watch what happens here, okay? See the sodium positive here? What's around it? These negative chlorines. And then what's around this negative chlorine? These positive sodiums. And what's around this positive sodium? These negative chlorines. So I hope you see how when nature has billions at its disposal, anytime it has the tiniest bit of sodium and chlorine, I hope you see how the positives are all surrounded by negatives, and all those negatives are surrounded by positives, and all those positives are surrounded by the negatives, and all those negatives are surrounded by positives. So that's how crystals form. All right. So I hope you have down that ionic compounds will usually be crystals. I'm not saying all crystals are ionic, but that's a pretty good guess. If you see a crystal, I would innately guess, yes, that's probably an ionic compound. That's not a bad way to start. Okay. So pick a second quadrant. The title for the second quadrant is types of elements involved. As I said, we're going to have 3 types of bonding. We're going to talk about this unit. So it'd be great for you to have down an ability to compare and contrast. How do I know what type of bonding it is? Well, it's going to be based on the elements that are doing the bonding. And there's 3 choices. Okay. So our first choice, the one we're going to talk about today, ionic bonds form between elements that have a very large electronegativity difference. Okay, so how would I know if elements have a very large electronegativity difference? Well, for a difference, I want them far away from each other on the periodic table. The farther, the more ionic. Okay, and really what that comes down to for us is that's going to be between metals and nonmetals. Metals tend to be on the left, nonmetals on the right, and that's going to help keep them far away from each other on the periodic table. Okay, the metals are going to lose electrons; they become positive, and that's because they have low ionization energy. Easy for them to lose. They're just kind of like, oh yeah, I've got electrons. I don't really care. Okay, nonmetals are going to gain electrons. They're high in electronegativity. They're like electrons, gimme, 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 gimme. So you get an element that's like, oh yeah, I got electrons, no big deal. And you get an element that says, ooh, electrons, gimme, gimme, gimme. And the two come together, and what's going to happen? The one that says, hey, this is no big deal is going to give electrons to the one that says, gimme, gimme, gimme. Okay. So what do you want to write down for how this is going to work out? You're going to want to be sure that you note we are looking, ionic bonding is going to be for a difference in electronegativity. We're looking for a pretty large difference in electronegativity. And that really works out to be between metals and nonmetals. Okay, metals are going to lose electrons. Metals are losers. So if I call you a metal, I'm calling you a loser. And nonmetals are going to gain. So I guess if I call you a nonmetal, I'm calling you a gainer. I don't know what that means, but I have no problem calling you metals. So be sure you get those parts down into your notes. Oh, no, I wanted to clear that. Okay. And in the same quadrant still, I wanted to, while we're talking about these crystals, I wanted to show you some crystal shapes. So here's crystal shapes. I am not going to ask you to know crystal shape names for the test. There's no reason for that at all. Okay, so not a thing. So I want you to see if ionic compounds are crystals. And crystals are trillions of positives surrounded by trillions of negatives, surrounded by positives, surrounded by negatives, surrounded by, I don't want to write that on paper. So what we'd write on paper is we would write a formula unit. A formula unit is the lowest whole number ratio of the atoms. Okay, so sodium chloride, a very typical salt ionic compound, is going to be 1 sodium to 1 chlorine. That's its lowest whole number. Now, I will never be able to go out into nature and start digging up in my backyard and find 1 single atom of sodium with 1 single atom of chlorine. I would never find that. If I find any salt in my backyard, it's going to be already, even the tiniest grain you can imagine, it's going to be billions of sodium and billions of chlorine. So we don't want to write that. So we write a formula unit. So you want the words, the vocabulary, the special vocabulary, you want vocabulary formula units written down there. And you want to know what that means. That is, it's the lowest whole number ratio. Okay. Going to clear this away. There we go. Okay, pick a third quadrant. We're going to talk about the strength of bonds. So eventually when we test, I'm going to tell you the type of bonding and expect you to know whether the comparative strength. Or if I tell you the comparative strength, know what kind of bonding it was, okay? And again, we're going to be able to contrast and compare our notes for ionic, metallic, and covalent, because we're all going to set them up the same with these 4 quadrants. So strength of the bond. Well, ionic bonding is considered to be very, very, very strong. Very strong. Ionic bond is between a positive cation and a negative anion. And being opposites, they stick together. And it's not just one positive and one negative. It's billions of positives and billions of negatives. So what if I gave you like 2 magnets stuck together? You could just pull them apart, no big deal, right? Okay. What if I gave you a block of 1,000,000 magnets stuck together and I said, shove your hands in and rip them apart? You wouldn't be able to do it, right? Okay. So the strength is based on the fact that we got so many cations and anions all coming together. What you need to know is that it's very strong, but how strong is strong? How not strong is strong? Okay, so we're going to measure that with this thing called lattice energy. So you're going to want to know lattice energy is the strength of how we measure the strength of an ionic bond. So have that vocabulary word down there and be sure that you write down its definition that is there on the screen.
Is this the same?
And then in the next quadrant, we're going to have properties of the compound. Okay. And in this properties of the compound quadrant, we're going to have the properties. And come test time, you would be expected to know from the bonding what properties to expect, or from a description of the properties, know what bonding to expect. Okay. This one is easy for me. You need to write down in your notes all of these 6 bullet points. So you're going to pause the video for a little bit. You're going to write them all down. It should make sense if ionic bonds are strong. It's going to take a lot of heat energy to separate them. So we're going to have high melting points. I mean, think about melting a salt. How many of you try to melt a crystal, right? You're like, oh, probably not, right? Imagine trying to boil it then. Okay, so lots of heat, high temperature needed. They're going to not conduct electricity. If you ever try to like take a crystal and use it in place of wire, spoiler, not going to do anything. Okay, not going to conduct electricity as a solid. We probably are aware salts will dissolve in water. Salts have those cations and anions, and water has a positive and negative end, and that works out really well. Positive to negative, negative to positive. The water can pull it apart. They dissolve very well. Now catch this, when dissolved or when melted, either way, the salts can transfer electricity. So I'm going to throw out the word vocabulary word, there we go, electrolytes there. And once the electrolytes unit comes in, that solutions in April, we're going to revisit this topic. But we call a liquid that can transfer that electricity to be electrolyte. Okay. Salts are hard. What do we mean by that? Well, if I had a crystal of salt in my hand and I squeeze it, am I going to do anything to it? No, it's there. Okay. So ionic compounds, because they're strong, they're going to hold together well. I can't squish it, right? Okay. What if I take a hammer and I hit it? Well, then something's going to happen, right? What's going to happen? It's going to shatter apart into pieces. We call that brittle. So our salts are going to break apart into little pieces. That is brittle. What am I like saying the opposite of here? Okay, well, what if I took the hammer and I hit it and it wasn't brittle? It would squish. So that would not be brittle. So by brittle, I'm specifically saying if you hit it hard enough, it's going to break apart into pieces. It's not going to squish or bend or anything like that. Okay, so based on these properties, if you just saw a list of these kind of properties, you should be able to tell me it's ionic bonding. Or if I tell you it's ionic bonding, you should be able to start listing me these properties. That's something you're going to need for the test. Okay, now actually we have a 5th topic to discuss, but this 5th topic is going to go on the back. So flip your whole notes page over, and on the back, we're going to talk about our 5th topic, and I'm going to label this special topics. Now, like I said, we're going to have ionic, covalent, and metallic bonding notes, okay? And you're going to compare and contrast. It's not going to work with this fifth topic. That's why it's going on the back. The other two sets of notes will have the first four topics, but they're going to have different special topics. So we will not have any ability to compare and contrast the special topics, but these are little things about this particular type of bonding that you need to know. So what I want you to know while we're on the topic of ionic bonding is I want you to know about a polyatomic ion. And it's always just confuses me. I don't understand. I ask students, how would you expect a polyatomic ion to bond? And they look puzzled and like don't know what to say. Like, do you not catch that the word ion is like right there in the name, polyatomic ion? Okay. So yeah, it's going to bond ionically. So what do you need to write down? You want to be sure you write down how a polyatomic ion, that is not, no, let go. Okay. You want to write down that polyatomic ion is a charged group. It won't behave. Come on, I give up. Why? Why? I don't know why. Okay, let me try again. Okay, polyatomic ion is a charged group of covalently bonded atoms. Okay, and then you want to please copy the pictures. These are pictures of polyatomic ions. And so in just a little bit, in our next unit, when we get to polyatomic ions and they're being used, I hope that you recognize, hey, that's a polyatomic ion and it will bond ionically. So you can see in this picture, it's got a positive charge. So somewhere in that picture, those elements have lost an electron. I'll never know which electron got lost. They all look the same. I would not know. But somewhere in that picture is one missing electron. And so it's got a positive charge. So what would stick to this positive polyatomic ion? Negative things, right? Okay. And somewhere in this picture, I have two extra electrons. It might be these two. It might, I don't know. I'll never know. They all look the same. Okay. But there's two extra, so it's a -2 charge. And with that -2 charge, what's going to bond to a negative polyatomic ion? Positive things. Okay, so have the definition of polyatomic ion written down. Pause the video as you need and write down draw the two pictures like you see, so that when we get to them again in our next unit, you have some understanding that when I say polyatomic ion, it will bond ionically. I don't know why that seems such a hard mental bridge, but that's how that works. So be sure you're building that bridge. Polyatomic ions will bond ionically. All right, that takes care of our notes over ionic bonding. You have other assignments to do, so be sure you continue working in Canvas on the other things that you need to do. And I will see you for some covalent bonding next time.